Okay, so back to the mass on a spring. All right, so we saw earlier that the mass spring system, we spend so much time looking at that because it's a useful physical model. Okay, we saw earlier that you could model atomic or nuclear vibrations, okay, with little masses on springs. So it's a really basic treatment, and you'll see also later on in your studies, but it just comes back to the idea of the treatment of oscillations, energy states. So this is our starting point. All right. Now, so remember, the whole idea was we couldn't use equation number 2. Okay, remember equation number 2? If we wanted to ask what's the position x for this block as a function of time, right? So the idea is the equation of motion from chapter 2, these only held when the acceleration was constant, okay? Here, the acceleration is not constant. You let this thing go, it speeds up from here to here, and then it puts on the brakes and slows down, turns around, speeds up from there to there, puts on the brakes here, and slows down to a stop. So the acceleration is definitely not constant, and we can't use equation number 2. Okay, so we need to find a version of equation number 2 that tells us the position as a function of time. Okay, we saw it before, but I didn't really derive it. Okay, so we want to find the position as a function of time for the oscillating block. Okay, so I'm going to start with F equal ma in the x direction. Okay, so the only force that acts on this thing in the x direction is the spring force. Okay, so remember, the Hooke's law of spring force is minus kx, so I put in minus kx. Okay, so I solved this for a. Okay, so I just solved that for the acceleration. Okay, so we're going to see in this chapter that this is a property of simple harmonic motion. Okay, if you find that the acceleration is proportional, okay, that thing means proportional, the acceleration is proportional to minus, okay, the position, then you have reason to believe that you have a simple harmonic oscillator, and it exhibits simple harmonic motion. Okay, so that's the form that we're going to be looking at. Okay, so I wrote acceleration as the second derivative of position, so I put that right there. Okay, I have that there. All right, so this equation is a differential equation. All right, so I know differential equations is not a math prereq. All right, but if you just take a block and attach it to a spring, you have to sit through calc 1, 2, 3, linear algebra, and differential equations. Okay, so there's a lot of math wrapped up in nature. All right, so this equation, we're not going to be responsible for solving it, but I want to show you techniques of solving it and patterns to see. All right. Okay, so it's given a fancy name. Okay, it's a second order differential equation. Second order because I have the second derivative. All right. It's linear because the variable x is raised to the first power. Right. It's ordinary because later in calc 2 or 3 you'll see partial derivatives. Okay, so it's just regular derivatives. Okay, so it's just given a fancy name. Okay, so in differential equation class, they will teach you how to solve differential equations that have a certain pattern. Okay, and here's the pattern. Pattern is you have a function. Okay, or you have a function x. All right, and you take two derivatives, and you get minus a constant times the same function back. Okay, so what we do is one way they teach you how to solve these in differential equations is you guess a solution out of thin air. Okay, now we're using a little bit of insight to guess a solution out of thin air. Okay, and the insight we have is here's a function x, you take two derivatives, you get minus a constant times the same function back. Okay, how many functions do you know that you can take two derivatives and you get the function that comes back? Well, sines and cosines remind you of that, right? Take a derivative of sine, right? You get a cosine, take a derivative of cosine, you get a minus sine, so you went from sine to cosine back to sine with a minus sign. If you start with cosine, go from cosine to sine back to cosine. Okay, there's a minus sign in there, but the function still looks the same. Okay, so we're going to guess this out of thin air, all right? Now, you'll see why I have the square root there. Okay, remember phi is just the phase constant. Okay, now, how do I know if that guess even works? Well, you plug it back in here and you check. You take two derivatives of this function, okay? Take two two derivatives of that function with respect to time and see if you get minus k over m times the same function back. All right. Okay, so let's take one derivative. Okay, I'm going to take one derivative with respect to time of that. Okay, so the x max stays here. Derivative of cosine is sine. Okay, the argument still stays the same, and I get well, a derivative of cosine is minus a sine. Okay, and then I get that square root that comes on the outside. Okay, so that's my first derivative. Right? Now I'm going to take the second derivative of that. Okay, so derivative of sine is cosine, minus sine stays there. I get another square root of k over m that comes outside. All right, and if I clean this up a little bit, okay, square root times the square root, that gives me k over m. Oops, and my x max is missing. I'm going to throw in my x max. There's my x max. Okay, and I still have my x max. Two square roots gave me that. All right, but if I look at that much of it, okay, that's this stuff right here. That's my original function. Okay, x max cosine of all that is my original function. So what I did is I guessed that function satisfies that requirement. Okay, I took two derivatives. There's my two derivatives. I got minus that constant. There it is right there. Times the exact same function back, right? That x is that whole thing right there. Okay, all right, so that means that that solution works. Okay, now kind of looking back in hindsight, you can see why we chose to put that square root in there, because you're going to take two derivatives and that thing's going to come out twice. And if it comes out twice, it'll get rid of the square root sign, and then you're going to have that thing sitting there. Okay. Okay, now, the other thing we can do to clean this up is we can look at the units of k over m. Okay, so remember, k is the spring constant, has units of newtons per meter. M is mass, kilograms. So a newton is a kilogram meter per second squared, and there's my m right there. I got the kilogram on the bottom. Okay, so the kilograms cancel, the m's cancel, and I have an s squared, which I'm going to write like that. Okay, then what I'm going to do is I'm going to write the word radian in there for free, because the radian is a dimensionless quantity. I can stick it in, I can take it out. Okay, okay, so that says that k over m has the same units as radians per second quantity squared. And what is a radian per second? That's a unit of angular frequency or angular speed. So k over m has the same units as omega squared. So we're going to call this stuff k over m. We're going to call that omega squared. So k over m has units of omega squared. Okay, so take square root of both sides. Omega is the square root of k over m. So way back here, okay, when we had this, which I'm going to rewrite, so d squared x dt squared is minus k over m x, okay. This right here, I'm going to call that omega squared. Okay, so that's omega squared. So this now I can write more compactly. Okay, so now we know the solution to this is the one we guessed before, but instead of having that messy square root in the trig argument, I'm just going to write it as omega. Okay, so the solution to our original differential equation is that where I have to put in what omega is. Okay, omega is the square root of k over m. Right, so essentially this tells us where that block is as a function of time. Okay, I can't use equation number 2, okay, because the acceleration is not constant. Okay, way back up here, okay, this says the acceleration is not constant. Okay, the acceleration depends on the position. Okay, so that's why we had to find a whole new equation of motion for this simple harmonic oscillating system. Okay, so we get rid of that, can't use that, but that becomes our equation 2. That tells us where the object is at any time. Okay, and remember, omega is that angular frequency. And I think I'd showed that if I have, let's say, a ball on a rotating wheel, okay, as that thing goes around, all right, and if I shined a light from the side, there's a light. If I shined a light at it, okay, and I looked at the shadow of the ball on the wall, that wall is the ball is going to go up and down. Okay, that shadow is going to go up and down in superharmonic motion. Okay, and that shadow is going to look exactly like a mass on a spring going back and forth. Okay, so we showed that's the close relationship between circular motion, okay, and simple harmonic motion. Okay, so we showed for a simple harmonic oscillator that if the equation of motion, okay, has this form, okay, so the position as a function of time, okay, that's x, the position of function of time, okay, that function requires that you take two derivatives, okay, you end up getting minus a constant times the exact same function back. So that has this form, right? Here's your function. You take two derivatives with respect to time, you get minus a constant times the exact same function back, okay? So that was the motivation for why we picked cosine in the first place. Because you take two derivatives, you get a cosine back with a negative sign, okay? All right, and I'm ignoring the phi for now, okay? I don't need to write omega t plus phi, all right? Okay, and I kind of alluded to, well, you take two derivatives, you get back to cosine with a minus sign. Same thing works for sine, okay? So if we had chosen that as our guess, all right, take one derivative with respect to time, because I want to take this function, put it back in here, okay, meaning take two derivatives, and see if I get minus a constant times the same function back. Okay, so I take the first derivative, okay, the omega comes out, okay, derivative of sine is cosine. I take my second derivative, derivative of cosine is minus a sine. I get another omega on the outside. But this right here, x max omega sine of omega t, okay, that's our original function x of t. So for this, I'm just going to write x, okay, and then that has the form that we want. Here's a function, take two derivatives, you get minus a constant times the same function back, okay, so that's what we did. Here's our function right there. I took two derivatives, I got minus a constant times the exact same function back. So the sine function works. Okay, well, sine and cosine are both periodic. So let's try another periodic function. What about the tangent? Okay, why didn't we guess that the position as a function of time goes as tangent instead of sine or cosine? Okay, so I take one derivative with respect to time. Okay, so derivative of tangent, I get an omega that comes out, and derivative of tangent is secant squared. Okay, I take one more derivative. Okay, so I'd get an omega come outside. Okay, what's the derivative of secant squared? I have no idea, right? But it's not minus tangent. Okay, so that doesn't work, all right? Well, what if we tried, okay, because the idea is you want to pick a function where you take two derivatives and the function doesn't change much. It goes from cosine, sine, back to cosine. Sine, cosine, back to sine. Okay, tangent didn't work. Well, what about the exponential? Okay, you take derivatives of e to the x, it doesn't change much. So what if I chose that as my position function? Okay, and let's test it. So I take one derivative, okay, I get omega that comes outside, okay, and then I take a second derivative, I get another omega, looking good so far. That's my original function right there. So for this function, I'll put in what x is. I mean, that original function is x, okay, but that has the wrong form, right? I'm supposed to take two derivatives, get minus a constant, which I don't have, times the same function back. So that doesn't work because there's no minus sign right there, okay? Now, what if instead of e to the omega t, what if we try a minus sign? Okay, try minus sign. Okay, I take one derivative, I get a minus omega, comes outside. Take a second derivative, I get another minus omega, so I get omega squared. There's my original function, x, and that doesn't work, okay? Because I took two derivatives and I didn't get minus the constant, okay? So that doesn't work, all right? Well, we were on the right track with the exponential function, okay, but the e to omega t didn't work, e to the minus omega t didn't work. So what you do is you try e to the I omega t, right, where I is the square root of -1. Okay, and you saw this in algebra class with I, and then you probably did this in Calc 2 when you did power series and Maclaurin series. Okay, so let's try this one. So I'm going to take one derivative. Okay, the I omega comes outside. Take a second derivative. I get an I times an I. I get another omega. Okay, I still have this. I squared is -1. Okay, so I squared is -1. That's my original function. Okay, so my original function, x of t, all right? And then I'm left with minus a constant times the exact same function back. Okay, and that would also work if we used e to the minus I omega t. That would work too. Okay, so this has the form is I take that function, take two derivatives, get minus a constant times the same function back. Okay, all right, why does that work? All right, well, you know from Calc 2, Euler's formula, when you did Maclaurin series and power series, okay, when you wrote the Maclaurin series for e to the I theta, okay, it was a combination of the power series for cosine. Okay, cosine has the even terms, and it has a combination of the terms from sine. Okay, and the sine has the odd terms. All right, but when you put in an I, you get the real part and you get the imaginary part. So e to the I theta is cosine theta plus I sine theta. Okay, so if I wrote it in terms of what we had up there, e to the I omega t, you have cosine omega t plus I sine omega t. So it's no surprise that originally that sine and cosine both work, okay? Because if up here, if e to the I omega t works, then sine and cosine will also work, okay? All right, so here's our oscillating system, okay? So in this picture here, maybe that was the equilibrium position and someone let it go over here at x max. So at time equals 0, okay, it starts here, okay, at the amplitude of x max, all right? So you could say this looks like a cosine, okay? So I just plotted the time, or the position of this mass, okay, as a function of time, all right? So what I did is I went to this one point, okay, at a certain time, and I waited until it came back to the exact same position heading in the exact same direction, okay? So from that time to that time, okay, that's when the motion repeats itself, okay, that's the period. So if this is time t, okay, this point is time t, that point is time t, okay, that time, plus 1 period, all right? So we know that the sine and cosine are periodic in 2 pi, all right? So we'll see that if I write the position, okay, this graph says that the position at time t is the exact same as the position at time t plus the period. Okay, so I have a relationship between the position at time t and the position at that same time plus 1 period. Okay, where that's the position function I'm using. All right. Okay, so I just put in what x of t was. X of t is that. Okay, it's that right there. And then on the right side, I put in x of t plus the period. So everywhere I have a t right here, I'm putting in t plus the period. So right here, I have t plus the period, okay? And then on the right side, all right, on the right side, I just multiplied this out. I have omega t, plus omega times the period. I just wrote that over there, okay? All right. Okay, so I want to look to see what I have here. So on the left side, I have cosine omega t plus phi. On the right side, I have a cosine of omega t plus phi, plus this extra stuff, okay? So I'm lining it up like we did in trig class, okay? Now, what is that? Okay, I think that's your lab partner, right? So from trig class, okay, this term is here, that term is there. So you know that the cosine of anything, like your lab partner, okay, is the same as the cosine of that same anything plus 2 pi, okay? Because the cosine is periodic in 2 pi, all right? So that says if I match these up from trig class, okay, that argument and that argument's the same, then this thing left over must be 2 pi. Okay, so this stuff must be 2 pi. So omega t is 2 pi. All right, so divide by t, the period, that says omega is 2 pi over the period. Okay, and again, that's no big surprise because remember, definition of omega is angular displacement with respect to time. So if something is going around in a circle, like a unit circle, okay, it goes around once, okay, the angular displacement is 2 pi radians, and the time it takes to go around once is the period. So for once around, right, 2 pi radians, and the time it takes to go around is the period. Okay, so I can either write it like that, or I can write it in terms of the period. All right. Now this reminds you of trig class. Okay, so when you did this in the middle of trig class, all right, they wrote it like this. Okay, when you were graphing the trig functions, they wrote y. Okay, when you're graphing y versus x, okay, they wrote y is a plus cosine of bx. All right, and what was that a called? They called the amplitude, and they used the letter a because they're worried that you'd forget that what that thing stood for. So a stands for amplitude. Okay, and then what you had to memorize in trig class is this thing next to the x. Okay, that b. Okay, when you calculate the period is 2 pi over that thing. So the period is 2 pi over b. All right. Well, now you know, right, that when something has this form, we have x is x max cosine omega t, okay, that the period is 2 pi over that thing, right? It's 2 pi over omega, all right? Okay, and we saw previously that the frequency f is 1 over the period, all right? And the angular frequency was related to the frequency via that 2 pi.